Good morning, everyone. We are from the Vision aka Knowledge Group. I'm Nicholas, and my groupmates and I, which are Wadi and Kamwai, are here to discuss our forecasting model. First, we need to obtain basic statistics of the SG temperature data. The picture on the right illustrates the function of how to collect the statistics. This picture also displays the statistics for train and test separately. Second, we need to use the mean and standard deviation to normalize the data for both train and test datasets. Here we are using x minus 29764 divided by 5851. This is to ensure the mean of the transformed data is about 0 and most of the time of the size less than 1. Lastly, we need to run calculation for the persistent model after normalization for us to easily compare the results and the model output. We use a factor of 5 since we are using CAFE. We then chose the smaller of the two value, which is 0.465, the number that we need to beat in our forecast.
Three features are used for better learning. They are the mean and standard deviation of window t minus 5 to t plus 0, and the difference between t minus 20 and t plus 0. Our network model consists of 4 layers neutral network with reduction of 1/2 in successive layer. ReLU saturator is applied in every perceptron. Dropout is also applied to prevent overfitting. We use difference network in this model for better learning. The deploy and solver are defined as given in Lab 2. Early stopping is allowed with 25 in length and 20 skips. In config.m, the dropout probabilities are defined as 0.05, 0.1, and 0.25. The sizes of neutral network are 32, 64, 128, and 256. The input size of 20 is chosen based on the window size. Maximum 10,000 iterations ensure the sample size is sufficient to allow early stopping to occur. Furthermore, Adam solver is chosen and 5 repeats is applied for each configuration.
Next, in the third part, I'll explain about the results presented by our board. As we can see from this loss graph, the persistent loss is 0.465 and the test losses are much lesser than persistent loss. The range is around 0.023 to 0.065, which is very promising. Next, these are the few configurations with the lowest test loss in our experiment. The best configuration is this, number 36, test loss of 0.023, input size 20, dropout probability 0.25, solver type Adam, neural network size 256. Okay, these two figures are actually comparing the results between actual and predicted data for training and tests. As we can see, both figures show good overlapping between actual and predicted values, which indicates quite good forecasting results. Okay, this is the scatter plots for training and test predictions. For a perfect prediction, the scatter plot is actually quite a straight line intersecting the origin. As we can see, most of the points produced by our forecasting boards lie around a straight line, which indicates a good forecasting. This lag correlation figure shows us whether our forecasting result is lag or not. If the peak is at the x-axis of greater than 0, then the forecasted result is lag. For this one, as we can see, the peak is at 0, which indicates not much lag for the results. Okay, in conclusion, the techniques used are normalization, persistent loss as benchmark, 3 features, windowing, 4-layer neural networks, value saturator, dropout, and difference network. The best configuration in our experiments are input size of 20, solver type Adam, neural network size of 256, and dropout probability of 0.25. Some of the possible improvements are using regularization and more repeats on the board. This is the end of our video. Thanks for listening.